date, OpenFOAM looks scary because it has no buttons, but it's just 3 folders, as you can see here. Once you know them, you kind of own them. First, the system folder is the brain, the control dictionary file, the fvSchemes, fvSolution, these stay there. Then there's the constant folder, essentially the physics, the mesh resides here, and the fluid properties along with the turbulence model that stays there. And the zero folder, it's the starting line, essentially. It's where your simulation starts from. So understanding how to set up your CFD analysis comes from understanding how these 3 individual folders work. So today we'll see that.
So now that we're done with the meshing, let's talk about the case setup itself. The 3 folders in question here, this is 0, constant and system. Let's take a look at these individually. So the first file we have, this is epsilon. Epsilon essentially talks about the dissipation rate of your turbulence kinetic energy. The calculation goes through the turbulence kinetic energy itself, where we estimate an initial, let's say, turbulence intensity of 5%, to which we can calculate the K, and by making use of the turbulence intensity and the mixing length, we can still estimate the value for my epsilon. A better way to do this is essentially to estimate this using the turbulence kinetic energy boundary condition for your both epsilon and K using the turbulence intensity. So OpenFOAM does it by itself, but maybe we'll do that in the next iteration. The next file, this is the turbulence viscosity, ut. We keep everything as calculated, and next is the pressure. We could still keep it as 0, but it doesn't really matter. The pressure value is just used as an initialization, nothing more than that. And ultimately we have velocity of 20 meters per second in the z direction. So there's that. Now let's take a look at the constant folder constituents. There's the turbulence properties. Here we have defined the RAS with K epsilon model, turbulence set to on, and the print of coefficients. And we have the transport properties. This is set to air with the kinematic viscosity set to 1.5 10 power minus 5 meter square per second. Coming to the system folder, we have all of these files here. We've already discussed the block mesh, the snappy, and the surface feature extract. The mesh quality dictionary file is also associated with that. Let's take a look at the other 3 files. The first file we have, this is the control dictionary. In control dictionary, we are using the simpleFoam solver. This is for steady state analysis, starting at 0, end time at 5000 with every 1 time step, or rather 1 iteration, since there is no time marching that is happening here. We'll write the solution for every 100 seconds or 100 iterations, and we'll remove the previous 2 solution files so that we are not storing the solution for every single time set. At the same time, we have the force coefficients, which is written in the functions subdictionary here. We are essentially calculating the forces around our wrench here. So the reference velocity, reference density, the center, reference center, and the lift direction, the drag direction, pitch axis, etc. Everything is provided here. Understand that the reference length and reference area need not be fully accurate. They just need to be a reference area, and OpenFOAM will calculate based on the cells present within that particular patch. For us, the wrench, and the surface area, the reference surface area, will be calculated on its own. So this is just for an initialization. Next we have the fvSchemes. This is the numerical schemes, how we define them. So steady state and everything else pretty much remains close to what we actually set it up as. We have our bounded gauze. We essentially try the boundedness for turbulence properties, because we don't want them to go below a 0 value that would blow up the solution, so to speak. So to avoid that, we're essentially using that. And if we were using the omega model, we could still add this, and we would need to add 1 wall distance. That is for understanding how near the wall your omega is going to get calculated, the default being the mesh wave type. The final file that we have, this is the fvSolution. fvSolution talks about your multiple linear solvers for these field variables. What type of solver are you using here? So for instance, the GAMG, geometric agglomeration method. Similarly, for the velocity and the turbulence parameters, we just have the smooth solver because we don't expect the turbulence properties to have as many, or rather have asymmetry in the solver metrics. And we have this simple loop provided here. So since we're using snappy hex mesh, I still have at least 2 non-orthogonal characters here, and a reference value with the reference cell set to 1E5, the same value that we did for our pressure, and the relaxation factors that are present here. You could still add one for pressure right here with the fields if you want to. If not, that's fine as well. So that's about the case setup. Tomorrow we will run the case setup itself and try to understand how the results look like, at least the initial ones. So see you tomorrow.